continue. Okay, let me open the table of content first. Okay. Okay, we are on chapter 18. Still on homework simulation here. Let me open that. Okay, this one. We are still on this section, homework simulation, basically trying to understand how to translate virtual to physical trace using the patching technique with linear page table. So I'm assuming we have other kind of page table, but in this chapter we will using linear page table. Okay, we already take a look at question 1, question 2, and now we are taking a look at question 3. To be precise, in this configuration of the simulation script, let me open that. I think in this one, okay, this is the representation that I used previously. Basically, we get the virtual page number first, and then we get the page frame number after we get the virtual page number, and then we get the offset, and then we do some calculation here. This one is to get the base address of the page frame, and then this one adding the offset into the, what is it called, the offset into the base address of this page frame. So this one, page frame number, is like the index for the page frame table or something like that, if I understand correctly. Similar to this one, virtual page number is the index for the virtual page table, and then after this, after we are adding the offset into the base here, we got the actual physical address or something like that. Okay, and this is the script. I actually adding a new option here with extra info. Okay, basically if we use the, what is it called, the dash uppercase C, we will get this information too. So for example, not Vim. VM patching, okay. Page size is 1K, address size is 16K, and then physical size is, we can use 32K, but in this case maybe I will try using the 2 megabyte or something like that, and then verbose, and then the percentage usage of the virtual address. Let's use this one or maybe this one, I guess, 25%, and then we can do some calculation like this, right? And if I'm curious, what is it called, how we can get this conclusion, right? How we can get this answer, I can add this flag. So this will add the information of this translation, something like that. It is just a little bit of changes for me, I guess. Okay, let's try this one. 75, okay. How many is this? Oh, okay, interesting. Wait, what? Is every address valid? Oh, interesting. Okay, let me check this first. Virtual address, right? And then I need to get the virtual page number. Okay, let me think. To get the virtual page number, okay, we do the masking, right? Okay, with virtual page number max, in this case, where is it? This one. Yeah, maybe let's put this in the variable. Yeah, I'm still not sure why we got this. Is this? Oh, wait a minute. Limits.its not integer max. Or maybe. Oh, is this the maximum value for unsigned integer? Let me check. Okay. This looks like the same. Alright. Maybe this one is the maximum value of unsigned integer. Maybe. Yeah, in max, maybe something like this. And then, yeah. Okay. In max, masking with the, what is it called? Complement of page max, and the page max is this one. Basically getting the maximum, I mean getting the page size, right? Getting the page size and then -1. This is to get the maximum value in one page, maybe something like that. In this case 1023, something like that. sorry. Okay, we cut that, and then VN Max. Okay, we got the base address for the virtual page. If we take a look, yeah, I already made this table or maybe list, something like that. The range when we have address space, address space size 16K and page size 1K. Right, I should put the information, put the 16K here. Yeah, maybe this one. And 1K in this one is this one. Yeah. Okay. 14. 14, and yeah, I kind of forgot where we get this number. This is 16, right? I think this one. That is 4. Oh. Maybe we got that from the exponent here. Like the address space size exponent is 14 and the page size exponent is 10. So 10 negative, 14 minus 10, right? And then equal 4. So there are 16 pages in the page table. Maybe something like that. Rather than using this information or having that information, let's add this information instead in the friends. In one page above, we got 16 pages in the page table. From the calculation of the exponent from address, the space size, and the space size and page size. Example, the space size 16K can be translated to the power 14 with the exponent with 14 as the exponent, I guess. And then bit size 1K can be translated to that one 10, something like this, with 10 as the exponent. So if we subtract the exponent from address space size and bit size, it will become 14 minus 10 and the result is 4. Okay, so the total bits in the bits table is 2 power of 4 equal 16. Okay, maybe something like this. Okay, okay, we got this one, right? What is it called? The representation at the base address in the virtual bits table. Okay, it is right this one. Okay, and then we need to, what is it called? Okay, let me show this, I guess. The representation in the binary is something like this, and we need to, what is it called? Remove this, I guess, something like that. How many? 12. Okay, so how do we do that? We are doing right shift, which is basically like dividing 2 into this number. Wait, and it becomes something like this. It is similar to this one. So 2 power 10, and then using that result to divide this number. Okay, and then we got this one. I'm kind of curious, can we do this? Oh, okay. Yes, so it become like this. Wait, this is 12, right? Okay, I assume this should be 16. Can we do this? Okay. Right. Maybe not 16, but 14, okay. Something like this, and because this is the prefix of the binary, we don't need this one, so it becomes something like this, if I understand correctly. Okay, something like that. So it is 4, virtual bits number 4. Let me check. Okay, it is valid, I assume. Okay. Right, and then if I remove this, is this correct? Let me check. Okay, this one, the leftmost bit here, the leftmost bit or the high order bit is the valid bit. So if the leftmost bit is 1, the rest of the entry is the page frame number. Something like this. Okay, let me put this. Alright, still the same. Page frame number, this one. And then is the representation, the offset. Okay. Let me think, how do I get the offset? By removing the virtual page number bits, right? So so the virtual address here right, and then using masking with the page mark, and if I remember correctly, the page marks is something like this. Basically, what is it called? Basically the page size -1, if I understand correctly. The maximum here, the maximum value in one page, I guess, something like that. I mean, for example, if I do this, right, n-1, so this one, what is it called, is 1024 item or something like that. There is that. Okay, masking that with this one, 171. So the offset is 171, and then okay, the base address. What is it? From the page frame number, right? The page frame number is, let's see if we take a look at this binary representation, something like this, and then we are shifting that to the left. Wait, no, not that one, but this one to the left by 10, because this is the exponent for the page size. Or maybe we can just, I think, multiply by this one. Let me check. Okay, right, is this the same? Okay, now, okay, this is the base. Maybe let's call this base address, base frame address, something like that. Maybe, or yeah, let's call this base frame address. Base frame address. Oh, yeah. And then adding that to the PFA offset, right? And then becoming this one. Okay. How do I get the information? Maybe something like this. Stand for base frame is the base address of the page frame number. So with PFA this offset, we are adding the offset into the base address of the page frame number, something like this. Okay, got this base frame address, and then okay, offset, offset again. $171. Okay. Is this the same? At least for now it looks like this is the same, but maybe in some cases this might not be the same. Yeah, let me check. Bitwise operation or use for is this it? Wait, or maybe it's like addition in decimal operation. Okay, maybe this one. Say I have for 32 bits number defined so that their bits don't overlap. That is something like this, wherein its number 1 could have anything in the place of the FF is its number 1 could have anything in the place of the FF here. Am I right in saying that addition and bitwise OR would always produce the same output for such sort of number? As a third alternative, you could also use exclusive OR, the caret here operator. But note that if you want to combine such number into one, it is good style to use bitwise OR. As long as two number num and num2 applies. Oh, then follows num1 plus num2 equal num1 bitwise OR num2. The reason for this is that addition is basically a bitwise XOR plus carry bit. But as long as there are no carry bits, num1 bitwise and num2 equals 0, then addition boils down to bitwise XOR, which is again because of num and num2 equals 0. This is logically equivalent to a bitwise OR. Yes. interesting. A bitwise. Okay. Let me copy this in the chat. Is anyone wants to take a look? Bitwise XOR plus carry bit. Oh, interesting. Yeah, I haven't observed that yet. How do we check this? Yeah, well, let me put this in the question, I guess. How to recheck? How do we check if addition is a bitwise XOR plus carry bit? If decimal addition is 1 is a bitwise XOR a carry bit, maybe something like this. Yeah, this is the question. But as long as there are no carry bits, num1 and num2 equals 0, addition boils down to bitwise XOR. Again, logically equivalent to bitwise OR. Okay. That is greater than 0 and having overflow, affecting the bits to the left. So in your case, both are equivalent, but you should go to the safe side and choose the less error prone one. Okay. No, because as long as you ensure that you only add things together where you know that they don't have the same bit size, you should be safe. Of course, as long as you ensure that you only add things together where you know that they don't have the same bit set. Oh, interesting. Wait a minute. If I do this, this one. Yeah, we don't need that. Right. Oh, interesting. The binary, both plus. Okay. Yeah, let me check this too. Okay, and then this one. Whenever the bitwise addition adds more than 1, either because the source have term or the carry from another place is 1 too, then a carry is produced and one place affect the other, as long as in an addition there is at most one added. Things are the same as bitwise OR. There is at most one added. At most one added. If I do this, is it gonna be the same? Oh no, I don't think that is the same. Oh, interesting. Okay, at most one. I assume something like this. Okay, maybe, but yeah, no. Oh, wait a minute. Is it something like this? Yeah, no. Whenever the bitwise adds more than 1, because the source have term or the carry from another place is 1 too, then a carry is produced in one place affect the other, as long as in an addition there is at most one added. Maybe something like this. Wait a minute. Yeah, maybe using this as an example, right? Oh, okay. As equal 0, something like this. Okay. Interesting. Yeah, I'm kind of curious about this one. When we look at the ether circuit, carry is produced, all elements taking part in the circuit are the OR element. Addition and bitwise OR would be the same, as bitwise OR would include any bits in either. And normal addition would do exactly the same given the mutually exclusive nature of your bits. Ether electronic. Hello Rema. Welcome. I'm making my operating system too. I currently at PM, but currently having problem to jump to my kernel address. Oh, okay. I'm not creating my operating system yet, but I'm understanding about the operating system concept first by reading this book, Operating System 3 Easy Piece, and currently trying to understand how the paging concept work with the, with the linear page table. So if you are asking a question about how to jump to kernel address, I'm sorry that I cannot answer that yet. I'm still not sure how to do that yet. I'm learning the basic of operating system first. But good luck with your operating system. Okay, wait a minute. Ether or summer? Addition of number in many computer and other kind of processor. Ether are used in the arithmetic. Okay, they are also used in other part of the processor, where they are used to calculate address. Okay. Binary ethers. The truth table, right, is a mathematical table used in logic, specifically in connection with Boolean algebra, Boolean function, and propositional calculus, which sets out the functional values of logical expression on each of their functional argument. Okay. Sum and carry. Oh, okay. Well, let me copy this in the chat. Oh, okay. Good luck with your studies. Thank you. Yeah, so far I've been having fun, I guess, learning all of this concept, even though I get confused a lot. But yeah, it is kind of new experience, you could say, learning all of this, like trying to understand what's going on under the hood. Okay, well, let me read this on the next session. Yeah, okay, putting this here. So basically, on the next session, let's try answering this question before we continue into the homework simulation. Okay, so that's it for now. Thank you for watching and see you next time. Bye bye.